Okay, so in this problem we have a car driving at 30 meters per second and a helicopter behind it that's moving at constant altitude of 200 meters above the car and moving forwards at 50 meters per second in the horizontal direction. And the helicopter wants to drop a water balloon. That water balloon will also be moving with 50 meters per second along with the helicopter. And the helicopter wants to know at what distance behind the car should they be when she drops the balloon in order for it to hit the car. So there's a couple different ways that you could approach this problem, but one way that I think makes it a little bit easier is to think of yourself in a reference frame where you're moving at 30 meters per second along with the car. So you're watching this whole thing from maybe another car next to this car. And so from your reference frame, the car is not moving at all. The car is at rest. And the helicopter is moving at 20 meters per second relative to the car. And thinking about it this way makes the math a little bit easier. You don't have to do it this way. You can treat the car's velocity separately if you want, but this way is going to be a little bit faster. So if we treat the car as being at rest, then we only have to worry about the motion of the water balloon. And the water balloon is moving with essentially projectile motion. It has both x and y components of its motion. So we'll break up that motion into the x and y components. And so let's make some definitions. Let's call where the water balloon starts at as x equals 0 and where the car is as x equals d. So we'll say the water balloon starts at x naught equals 0, and the water balloon has some x velocity due to it coming from the helicopter that's moving forwards. That's 20 meters per second. And there's no acceleration in x, so the x motion as a function of t is just 20 meters per second times t. In the y direction, let's say we'll start, the ground is y equals 0, so the starting point is 200 meters. So y naught is 200 meters. V naught y is 0. The water balloon doesn't start with any initial vertical motion in the up or down direction. But then there is some acceleration, gravity pointing downwards, so minus 9.8 meters per second squared. So y as a function of t is 200 meters minus 1/2 9.8 meters per second squared t squared. Okay. So what we want to know here is we want to know the value of x of the water balloon when it hits the car, and that's when it hits the ground. But to know that, we have to know what time that happens at. So let's first go over here to the y equation and figure out what the time is when y equals 0. That is when the water balloon hits the ground. So let's see. So the water balloon hits the ground when y is 0. So 0 equals 200 meters minus 1/2 9.8 meters per second squared t squared. And we can rearrange this. You might want to do a few more steps, but so you can pause and work through the algebra on your own. So you should get t equals square root of 2 times 200 meters over 9.8 meters per second squared. And this should give you 6.4 seconds. So that's the time at which the water balloon hits the ground. And so we can go ahead and plug that time in here and say x of t equals 20 meters per second times 6.4 seconds. And so that should be 128 meters. So x equals 128 meters when the water balloon hits the ground. So what we're really saying here is if this water balloon is dropped from the helicopter, it'll take 6.4 seconds to reach the ground, and when it does reach the ground, it will fall 128 meters ahead of this helicopter. And so the helicopter wants to be 128 meters behind the car when it drops it. Okay, so that's the answer to that problem.